The river did not always run black. There was a time when its surface reflected sky, broken only by wind and the slow movement of fish beneath the current. But by the early industrial decades, something began to change in the water's behavior. First came discoloration at the edges, faint streaks of gray that clung to reeds and stone. Then came the odor, sharp enough to carry for miles downriver. Then, finally, the transformation that local communities could no longer ignore, a river that looked less like water and more like liquid shadow. At the center of this change stood a machine system so vast it was never seen as a single object, but as an entire industrial organism. A network of mills, discharge channels, chemical baths, and processing furnaces that converted raw material into profit with relentless efficiency. What it expelled, it did not destroy. It released it directly into the water system that sustained entire regions. Factories along the banks treated the river as something infinite, a moving container with no memory, no limits, no consequence. But the river remembered differently. Over decades, its chemistry changed, oxygen levels collapsed, aquatic life disappeared in waves that were too slow to be noticed at first, then too large to be ignored. Entire stretches became biologically silent, where nothing survived beneath the surface except suspended waste, drifting like industrial dust in liquid form. And yet production did not stop. Because this system was not designed to protect the river, it was designed to sustain industrial expansion at any cost, at any scale, under any condition. Engineers called it progress. Governments called it development. Investors called it growth. But downstream, communities had a different name for it, one that carried no technical language at all, only lived experience. Poison in motion. For nearly a century, this machine system operated across continents, hidden in plain sight, embedded into the geography of civilization itself. Rivers that once defined life became conduits of waste. Entire ecosystems collapsed quietly, without a single dramatic moment of failure. Only accumulation, repetition, and time. The question is not how it happened. The question is how something so visible was allowed to become invisible for so long, and what it means when a machine does not destroy a place suddenly, but slowly rewrites it until nothing recognizable remains. Before the river became dark, it was not yet free of industry. It was already being used, already being altered, already being asked to carry more than water should ever be asked to carry. But in its earliest industrial role, it was still treated as something living, something with limits that had to be negotiated rather than ignored. The problem began with production itself. In the pre-mechanized era of large-scale chemical and textile manufacturing, every stage of transformation depended on water, not as a passive resource but as an active medium. Dyeing cloth required repeated rinsing in flowing currents. Metal processing demanded cooling channels that could absorb heat faster than air. Paper mills relied on continuous washing cycles to strip fibers and chemicals from pulp. Even early tanning industries depended on river water to carry away biological waste that no settlement could otherwise contain. At small scale, these uses were survivable. A river could recover from scattered workshops, intermittent discharge, and seasonal production cycles. The water would dilute, disperse, and eventually restore equilibrium. But industrial demand did not remain small. As production intensified during the 19th century, the river was no longer a shared resource between towns and workshops. It became infrastructure, a moving extension of the factory floor. Every expansion in output required a corresponding increase in disposal capacity, and there was no practical method to store or neutralize waste at scale with the technology of the time. Factories solved this limitation in the simplest possible way. They removed it. Waste was no longer treated, filtered, or contained. It was redirected. Pipes were extended from industrial interiors directly into riverbanks. Channels were dug to accelerate discharge. Entire sections of river were engineered to maintain flow speed so waste would not accumulate near production zones. The logic was not concealment, it was efficiency. But efficiency created its own bottleneck. As production multiplied, so did byproducts. Coal processing introduced tar residues and sulfur compounds. Dye manufacturing introduced synthetic chemicals that resisted natural breakdown. Metal refining released heavy particulates that settled into sediment and never left. Each industry added its own signature to the water, and none were designed to cancel each other out. The river, once a system of balance, became a cumulative ledger of industrial output. Communities downstream began noticing changes before engineers acknowledged them. Fishing yields declined first. Then fish behavior changed. Migration patterns disrupted. Spawning cycles shortened. Then came visible pollution. Foam collecting along shorelines, unnatural colors spreading through slow-moving sections, and periodic fish die-offs that appeared without warning and disappeared just as quickly, leaving silence in their place. Still, these signs were treated as externalities. Because the real bottleneck was not environmental, it was industrial. Manufacturers faced a constant pressure that defined the era. Scale or collapse. Competition forced output upward. Labor systems were reorganized around continuous production. Contracts demanded fixed delivery volumes that could not be interrupted by environmental constraints. Any attempt to treat waste internally meant reduced output, increased cost, and loss of market position. So the river became the only viable solution, not because it was safe, but because it was available. The assumption underlying this system was simple and dangerously stable, that natural environments could absorb industrial excess indefinitely, that dilution equaled disappearance, that movement equaled cleansing, and that what could not be seen in solid form would not accumulate in consequence. This belief allowed entire industries to expand without designing for waste management at equivalent scale. Factories evolved around production optimization, while disposal remained externalized to geography itself. But geography has limits. As discharge increased, rivers began to lose their self-regulating capacity. Flow rates could no longer compensate for chemical load. Seasonal variations that once restored balance became insufficient against continuous input. The river system was no longer responding as a living ecosystem. It was functioning as a chemical channel under permanent stress. And still, no single factory was responsible for the transformation. That was the critical illusion. Each facility contributed only a fraction. Each discharge pipe carried only a manageable volume. Each company could point to others upstream and downstream. Responsibility dissolved into distance. What emerged instead was a collective system of output without ownership. A distributed machine built not from gears or pistons, but from repetition across geography. By the time environmental degradation became undeniable, the system had already scaled beyond the possibility of simple correction. Entire regions depended on industrial output for employment, infrastructure, and economic survival. To challenge the discharge system meant challenging the foundation of regional stability itself. The river, meanwhile, had become something new. Not a natural feature, not an engineered tool, but a continuous endpoint of industrial metabolism. And the question that emerged from this transformation was no longer about individual factories or isolated failures. It was about how an entire civilization learned to build production systems faster than it could imagine the consequences of what those systems would leave behind. The transformation of rivers into industrial conduits did not begin with a single invention, nor with a single decision. It emerged from a convergence of technologies, economic pressures, and institutional habits that developed unevenly across the industrial world, then converged into a shared operational logic. At the center of this convergence was a simple requirement: continuous production at increasing scale. By the mid-19th century, industrialization had reached a stage where production was no longer episodic. Mills, refineries, dye works, and chemical plants operated on near-continuous cycles. Steam power allowed machinery to run for days without interruption. Rail networks ensured raw materials arrived on fixed schedules. Urbanization guaranteed constant demand. The system was no longer experimental, it was structural. But continuity created a problem that older industrial models had never fully solved: waste accumulation. Early workshops had relied on limited containment: barrels, pits, sedimentation basins, and manual disposal. These methods worked only because production volumes were small and intermittent. As factories scaled up, waste generation grew exponentially, while disposal methods remained linear and labor-intensive. The mismatch became untenable. Engineers and industrial planners began searching not for elimination of waste, but for displacement of it. The solution emerged gradually through infrastructure adaptation rather than invention. Rivers, already used for transportation and milling, became the most convenient recipient of industrial byproducts. This shift was not centrally coordinated. It developed independently across regions undergoing rapid industrial growth. In Britain, textile mills along the River Irwell and River Aire expanded their dyeing operations without parallel investment in chemical containment. In Germany, early chemical industries along the Rhine began channeling effluent directly into fast-moving sections of water to prevent localized buildup. In the United States, steel and paper industries along the Ohio and Hudson rivers adopted similar discharge practices, driven by expansion pressure and lack of regulatory restriction. What unified these developments was not technology, but assumption: that flowing water could neutralize industrial output, that dilution was equivalent to disposal, that distance downstream equaled disappearance. By the time large-scale industrial corporations formed in the late 19th century, this assumption had become embedded in operational design. Waste channels were not considered secondary systems, they were integral infrastructure. Many factory blueprints included direct river discharge as a planned feature, not an improvisation. Municipal authorities often reinforced this arrangement. Cities growing alongside industrial zones faced their own sanitation crises. Without advanced sewage treatment systems, urban waste and industrial waste frequently merged into the same waterways. The river became a shared utility system, serving factories, households, and transport networks simultaneously. This convergence created an environment where contamination was normalized at scale. The Industrial Revolution did not simply increase production, it redefined what counted as acceptable environmental change. By the early 20th century, entire river corridors were structurally integrated into industrial economies. The Ruhr Valley in Germany became a dense network of coal, steel, and chemical production linked directly to tributary systems. The Thames in London functioned simultaneously as shipping route, waste channel, and industrial sink. The Cuyahoga River in the United States carried petroleum residues so concentrated that it would later become infamous for catching fire. Yet, at the time, these conditions were not treated as anomalies. They were treated as indicators of economic vitality. A productive river was not a clean river. It was a busy river. The machine that turned rivers black was not a single apparatus, but a distributed system of industrial dependency. Governments incentivized production to fuel national growth. Corporations expanded capacity to meet global competition. Workers depended on factory output for survival. Every layer of society reinforced the same direction: more production, more throughput, more discharge. Environmental impact assessments did not yet exist in meaningful form. Scientific understanding of chemical persistence in ecosystems was limited. Even when pollution was observed, its long-term systemic effects were poorly understood or politically inconvenient to acknowledge. This allowed the system to deepen without constraint. Technological advances only accelerated it. The development of synthetic dyes, petroleum refining, and large-scale chemical synthesis introduced entirely new classes of waste, substances that natural water systems could not break down or absorb within any meaningful time frame. Heavy metals accumulated in sediment. Hydrocarbons formed persistent surface films. Acidic compounds altered pH levels across entire river sections. The river ceased to function as a regenerative system. It became a conveyor of unresolved industrial residue. By the mid-20th century, the scale of integration had reached its peak. Industrial complexes were no longer located near rivers for convenience. They were designed around them. Entire production ecosystems assumed permanent access to flowing water for both input and output. Removing the river from the system would have required dismantling the industries themselves. And so the system remained. Even as evidence of ecological collapse accumulated, economic dependence prevented reversal. Pollution levels increased not through sudden escalation, but through sustained normalization of degradation. Each year added another layer. Each decade deepened the transformation. By the time the true scale became undeniable, the river was no longer a separate entity from industry. It was part of its operating structure, a silent extension of industrial design. And the machinery that had produced this transformation was not mechanical in the traditional sense. It was institutional, distributed, self-reinforcing. A system built not to destroy rivers, but to make their destruction an unexamined condition of modern production. The machine was never located in one place. It existed wherever industrial discharge met flowing water, wherever pipes ended at riverbanks, and wherever production systems treated liquid waste as an uninterrupted extension of manufacturing itself. Its structure was invisible in the conventional sense, yet precise in its engineering logic. At its core were three interconnected systems: production units, transfer infrastructure, and aquatic absorption zones. The production units generated waste as an inevitable consequence of industrial transformation. Chemical reactors, dye vats, smelting furnaces, pulp digesters, and oil refineries all produced effluents with distinct physical signatures. These were not incidental byproducts. They were continuous outputs, tied directly to operational cycles. From these units, transfer infrastructure carried material outward. This infrastructure consisted of pipe networks, drainage canals, settling channels, and reinforced outflow points designed to move liquid waste away from production floors without interruption. The scale of these systems varied, but their function remained consistent: maintain uninterrupted production by ensuring that waste never accumulated within industrial boundaries. Many of these channels were engineered with gradient precision. Gravity-assisted flow reduced energy costs. Pumping stations regulated pressure differentials. In larger facilities, multiple discharge lines converged into centralized outflow basins, where waste streams mixed before entering the river system. At the final stage lay the river interface. This was not a passive boundary. It was engineered exposure. Outflow points were positioned to maximize dispersion. High-velocity discharge ensured immediate mixing with current flow. In some cases, angled pipes introduced waste below the surface to prevent visible accumulation near shorelines. In others, cascading discharge steps were used to break flow into multiple streams, increasing turbulence and accelerating downstream transport. Once released, industrial waste entered a dynamic system governed by flow rate, temperature, sediment interaction, and chemical composition. In theory, dilution would reduce concentration. In practice, accumulation exceeded dispersion. Different industries contributed different loads. Textile factories released dye compounds that bound strongly to organic material in sediment. Metal processing plants released heavy elements such as lead, mercury, and cadmium, which did not degrade but instead settled into riverbeds. Chemical plants introduced synthetic compounds resistant to natural breakdown mechanisms. Refineries added hydrocarbons that formed surface films, restricting oxygen exchange between air and water. These substances did not simply dissolve, they stratified. They accumulated in layers within the river system, some floating, some suspended, some embedded permanently in sediment. The river, once a continuous flow of renewal, became a layered archive of industrial history, each layer representing a different phase of production intensity. The physical behavior of the system was deceptively stable on the surface. Flow continued, currents persisted. From a distance, the river appeared active, even healthy in motion. But beneath the surface, oxygen levels declined steadily. Biological activity collapsed in stages. First, sensitive species disappeared, then larger aquatic populations declined. Finally, microbial balance shifted, altering decomposition cycles and accelerating anaerobic conditions in deeper zones. The system maintained motion while losing life. That contradiction defined its function. Temperature regulation played a secondary role in the system's behavior. Industrial discharge often entered rivers at elevated temperatures, particularly from power generation and heavy manufacturing. Thermal pollution altered aquatic chemistry further, reducing oxygen solubility and increasing metabolic stress on remaining organisms. This created feedback loops. Reduced oxygen increased decomposition of organic matter, which in turn consumed even more oxygen. Chemical reactions accelerated in warmer conditions, increasing toxicity levels in certain compounds. Seasonal changes, which once provided recovery periods, became insufficient to reverse accumulated damage. Yet the system remained operational because it was not governed by ecological feedback. It was governed by industrial continuity. Monitoring systems, where they existed, focused on flow capacity rather than environmental quality. Engineers measured discharge rates, pipe pressure, and output consistency. Environmental indicators were secondary, often recorded only in response to visible crises rather than continuous assessment. By the time chemical analysis became more advanced, the system had already reached a scale where localized intervention was ineffective. Even if one discharge point was controlled, hundreds of others continued feeding the same network. The machine was distributed across geography. Its power lay in repetition. Each factory acted as a node. Each discharge point acted as an output valve. The river acted as the convergence channel. No single operator controlled the entire system, yet the combined effect was unified and consistent. This distributed design made the system resilient to interruption. Shutting down one facility did not stop pollution. It merely shifted load distribution downstream. The system adapted automatically, not through intelligence but through scale. Over time, the river itself changed its physical behavior. Sediment composition thickened with industrial residue. Channel depth altered due to accumulation of heavy deposits. Flow patterns shifted as vegetation along banks died and erosion increased. In some regions, the river's color became a semi-permanent characteristic rather than a temporary condition. What emerged was not a natural system impacted by industry. It was an engineered hybrid system, sustained by continuous industrial input. A river that functioned as both ecosystem and infrastructure channel, but could no longer fully perform either role. And at the center of it all was a simple operational truth. Nothing in the system required restoration, only throughput. The first people to understand the river were changing were not engineers. They were the ones who lived beside it. Fishermen noticed it first, long before laboratories confirmed anything. Nets that once came up heavy began returning light, then empty, then coated with residue that smelled wrong even before it was identified. Fish that did remain showed visible deformities, sluggish movement, and unfamiliar behavior, surfacing too often, dying too quickly, disappearing in patterns that followed industrial schedules rather than natural cycles. Downstream communities adapted before they had language for what was happening. Water was no longer trusted for drinking unless boiled, filtered, or transported from elsewhere. Washing in the river became rare. In some regions, entire towns began treating the river as a boundary rather than a resource, something to be observed from a distance rather than used directly. Yet, the industrial system surrounding it did not slow. Inside factories, the river was not discussed as an ecosystem. It was referenced as capacity, a disposal channel measured in flow rates and permissible limits. Operators focused on maintaining output consistency, not environmental stability. If waste left the facility, the system was considered functional. For workers inside these plants, the river's transformation was distant but not irrelevant. Waste handling became part of routine labor. Pumps clogged more frequently as sediment thickened. Maintenance crews worked longer hours clearing deposits from intake systems. Corrosion accelerated in metal piping, exposed to increasingly reactive effluent. Over time, even the infrastructure of discharge began to fail under the weight of its own output. And still, exposure increased. In certain chemical and refining environments, workers were not directly interacting with the river, but with the same substances that eventually entered it. Toxic compounds circulated through air, water vapor, and surface residues inside industrial spaces. Chronic exposure became normalized. Respiratory illness, skin conditions, and long-term organ damage accumulated across entire labor populations. There was no single catastrophic moment that defined the human cost. Instead, there was duration. Years of contact, decades of repetition, generations born into industrial regions where environmental contamination was not an exception but a baseline condition. The river absorbed industrial output, but the surrounding communities absorbed its consequences. By the mid to late 20th century, the scale of visible ecological damage forced institutional response. Scientific studies documented oxygen depletion zones, heavy metal accumulation in sediments, and long-term toxicity in aquatic food chains. Some rivers were declared biologically dead in sections spanning entire urban corridors. The system could no longer be ignored. Regulation followed, but unevenly. Environmental protection laws began restricting direct discharge. Industrial permits required monitoring and reporting. Treatment facilities were introduced to intercept waste before it reached waterways. These systems marked the beginning of a structural shift, but they arrived late relative to the scale of accumulation, because by then the river was already carrying a century of material history within its sediment. Some regions undertook large-scale cleanup efforts. Dredging operations removed contaminated layers. Aeration systems attempted to restore oxygen balance. Wetland reconstruction projects were introduced to rebuild biological filtration. Progress occurred, but slowly, unevenly, and often incompletely. In heavily industrialized corridors, full restoration proved impossible within practical timelines. The contamination was not superficial. It was embedded deep within geological layers of riverbed sediment. What had been added over generations could not be removed in years. Meanwhile, industry itself began transitioning. New technologies reduced reliance on direct discharge. Closed-loop water systems were introduced in advanced facilities, recycling industrial water internally rather than releasing it externally. Chemical processes were redesigned to minimize toxic byproducts. Electric and digital systems replaced older high-emission production methods. But replacement did not erase history. It only reduced the speed of accumulation. The rivers remained altered. Even where visible pollution decreased, chemical signatures persisted in sediment cores, Biological recovery remained incomplete, and ecosystem structures never fully returned to their original state. In many places, the river became something else entirely, not dead, but permanently transformed, a controlled system that required ongoing human intervention to remain stable. And alongside this environmental legacy exists another, less visible one: memory loss. Entire generations grew up beside rivers they never knew as clean. Industrial landscapes became normalized geography. The idea that water could once sustain unbroken ecological cycles became abstract, almost historical fiction in some regions. Only archival records, scientific data, and older oral histories preserve the contrast. And when standing at the edge of these rivers today, where cleanup has succeeded enough to allow partial ecological return, what remains most striking is not what is present, but what is missing. The silence where life once was dense, the absence beneath visible flow, the realization that the machine was never only about factories or pipes or discharge points. It was about time, a century-long accumulation of decisions that transformed flowing water into industrial infrastructure without ever requiring a single moment of collective awareness. And that is its final legacy. Not a machine that destroyed a river in an instant, but a system that redefined what a river could be, slowly, continuously, until even memory struggled to recall what it had once been.